It's a great pleasure to introduce our first speaker, Professor Manfred Broy from the University of TU München. Professor Broy has had many great achievements in computer science and software engineering. It's hard to make a survey of all of them in an introduction without taking over all of the lecture time. So in the benefit of allowing the speakers to speak for the most time, I will stay brief with the introductions. Professor Broy has been very active in introducing CPS in Europe. And in particular, he has emphasized the human aspect as part of the CPS point of view. More broadly, he has been very active in creating all kinds of organizations, academic organizations. So I don't know anybody else that has actually founded 2 faculties, for example, in addition to a lot of academic work. So it's a great pleasure to have Professor Broy here today. And without further ado, I will hand over the mic to him now. Welcome, Professor Broy.
So I will talk about systems, in particular cyber-physical systems, and of course these are systems where software plays a major role. And I will start with a very recent workout I received only 2 weeks ago. It's by INCOSE. INCOSE is the International Committee on Systems Engineering. And they have published a new draft white paper. It's not official paper yet, it's about to come. And it's interesting because they are interested in a new definition of systems engineering. So it fits very well to the topic of the summer school. And they say as a working premise and basis for discussion, they consider this strawman. And the strawman says, systems engineering seeks to understand societal needs for technology-enabled systems, services, and capabilities, synthesize holistic fit-for-purpose solutions, and facilitate their delivery and successful operation. And it's a 20-page paper which describes the strawman. And they discuss a lot of things very carefully. Interestingly, they don't talk about any formal stuff in their paper. And I will give you another part of this. They are about to define systems of interest to systems engineering. And this is, of course, closely related to the discussion what a system is. And this is very much what I want to discuss in my first lecture. And let's just look at what they define as a system. And they mean that it's interesting to look at 4 aspects or 4 variants of systems. They talk about what they call the situation systems, and just by the way, this is not my terminology, and I will not use this terminology a lot. I will switch to the terminology I'm used to. So they talk about a situation system. They also say it's known as context, and I will use the term context for that. Environment, problem, situation, or wider system of interest. They use this term wider system of interest throughout the paper, which I don't believe it's a good idea. The idea, and I will come back to that idea, is of course, whenever you study a system, it's also important to understand what is the environment, the context of the system. So to whom is the system talking to which other system it's interacting, and this is exactly what I consider important. Then they talk about the systems that does systems engineering. I would not call this a system, and I will not consider that, but of course these are the methods and techniques we use to build systems. And then the systems that is systems engineered, and this is exactly the system of interest. And I will talk about this situation system, what they call it, and the system that is systems engineers. And they talk about the system of structured information, the system architecture or system model. And I consider these 2 things close together. So I will talk about this, and I will talk about this, but I will not talk about this. But this is an ongoing discussion, and there's a lot of discussion on the web currently. So I will not go into deeper, but I just wanted to mention that to show you how important it is to have a clear understanding what a system is. And so I will talk in my first lecture about interfaces and systems. And it's interesting, in this paper, I think I did not find the term interface anywhere, which I think is just wrong. I believe to understand systems, especially the systems we are interested in, is a key there is to understand the notion of an interface. But before we go into that, let's look at cyber-physical systems. What are key properties and challenges? What's the difference? I'm working in the field for quite a while now. When I started to work in the field, I was mainly working in software and software engineering. And there the people were convinced that it's important to get rid of a lot of stuff and to abstract it away. And what was abstracted away was everything which was related to physicality. So software was considered as a pure logical artifact. And so there was nothing about physicality, nothing about real-world awareness, nothing about real time. By the way, one of the first interesting languages that were created, and to a large extent in my university, was ALGOL. And in ALGOL they decided not to take into account the print statements as part of the standard, because the print statement was considered not so important. That's interesting, because nowadays interaction is the key. And the only interaction that they had at that time was printing and reading. And this was considered not a standard, because they were completely concentrated on algorithms, and algorithms more or less completely independent of the physical world. But if you build software systems that are directly connected to the physical world by sensors and actuators, real time is a key, and probability is a key, because you are dealing with a world where probability is a good way to think about certain artifacts. So connectivity is an issue. Connectivity, first of all, between the software and the physical systems, but it's also interesting to consider systems of systems, to connect subsystems. In particular, nowadays, we are often in a situation where we connect subsystems which were built in a situation where we do not consider the other systems when we build it, but later we come up with the idea to connect them, and this is something we have to manage from a methodological point of view. So systems are connected to cloud services, to the internet, to the World Wide Web. This is another way of thinking about systems of systems. And if you think about systems of systems, you have to think about decomposition of subsystems and of services. And this is something I will try to approach in my lectures and give you a model how to do that. And of course then interoperability is a key. Today in practice people work a lot with what is called service platforms, and this is something to look at. When we go into from closed software systems which are just operating as algorithms on the machine, when we go into a more open way and connect systems with systems and connect systems with sensors and actuators, of course it is a big change, because we get into openness. And when we talk about openness, one issue is security. I will not talk about security in my lecture at all, but I just want to mention that security is a big thing. In the introduction it was mentioned that I'm very much interested in human-centric aspects. Again, in my lecture today I will not cover any human-centric engineering aspects, but we should keep in mind that this is an issue. And then there's a lot about dynamic systems, dynamic interfaces, dynamic architectures, dynamic change of behavior, which is sometimes called adaptivity. Also a very important part, which I will not cover. I will rather concentrate on what you see on the left side. And of course, if you talk about mobile systems, you have also to think about things like space awareness, and all this I will not cover. I will be interested very much to have a key approach to models for systems, in particular cyber-physical systems. And when we have to model cyber-physical systems, we have to capture a number of aspects. I already talked about that. Interaction. A key between, when we study systems, is the interaction between the system and its operational context. This is what I mentioned before. It's also interesting to look at the interaction between the subsystems within a system's architecture, and we have to understand the synchronization and orchestration of components and subsystems and systems together with their context, and this is very much related to protocols. And it's interesting that in computer science we did not really extend our notion of algorithm to this situation properly. If you look at a lot of the definitions of algorithms you see today, they are still the old idea of algorithms. Algorithms as a standalone thing without interaction. Of course, we have to understand that also protocols are algorithms, but they are algorithms which are not completely covered by the classical definition. We have to look at distribution, and distribution means elements of systems in different locations. I will not go into this very deep and just cover it at a very general logical level, because when you do a decomposition of systems into subsystems, in a certain sense it is from a logical point of view not so important whether these subsystems are together on one chip or whether these subsystems are on the web, and one is in Europe and one is in Asia. The logical questions you have to answer are very similar. There might be differences in time. I already mentioned this operational context, systems, environment, which is also mentioned by Nkose. I will give you some ideas about real-time and probability. And the key issues I am looking at are three: interfaces, states and state transition, and architecture, in particular the decomposition of systems into subsystems. So let's come back to what the thing I started with. What is a system? And this is a slide due to Michael Jackson. You know Michael Jackson? Yeah, there are two of them, and most people know the rock star. I can tell you a story. My little daughter, she's now not little anymore. I once had a group where Michael Jackson is part of it, as doing a meeting at my university, and we had a little dinner to begin with. And I said to my family, today I go to the dinner. If you're interested, you can come with me. And I said to my little daughter, Michael Jackson is around. And she said, oh, I will come. and then we went there. And Michael, who is a very nice person, I said to my little daughter, this is Michael Jackson. He said, this is not Michael Jackson. So I'm talking about the, for me, famous Michael Jackson from United Kingdom. He was a very successful businessman and software engineer in the late 70s and 80s. And now he is a very nice British gentleman, still working on an understanding what systems are. He's particularly interested in requirements engineering, has wrote a number of very nice texts about that, so I can just recommend that. A few years ago, he gave a talk where he used this as a description what a system is. And he's not talking about system. He has another terminology. He talks about the machine, he talks about user interfaces, and he talks about the problem world. This is just a different terminology. I will not use his terminology, but I want to ask a question, where is the system? He doesn't mention systems. And you could first think about the system as the software and the hardware, so the press controller architecture as being the system. And it is part of finding the scope. If you look at a particular application, and this is not a very complicated one, we can now define what is the scope. And I think it's very important, if you want to develop a system or study a system, first to think carefully about what is the scope. So what is part of the systems you consider and what is outside. And what is outside is called the context, at least that part of the world which is outside and which is relevant for the system, which you consider as part of what you are interested in. So this would be one possibility. So you could ask the question, is the hardware software the system? Of course you could say, no, I'm only interested in software. And then you would say, is the software the system? And the next possibility would say, no, a system is something which is physical, real world. So I consider the actuators and the sensors and the press mechanisms and the operator controls and the lamp and the switches. This is for me the system. So the system is the mechanical part of what I'm considering. And I consider this a system. And the next step would be to say, well, I'm interested to think about this part of the system, which is the press controller architecture, but I add the actuators and the sensors. So what is the difference? What I had before in the beginning, here I have digital interfaces. If we do it like this, I have non-digital analog interfaces. So it depends where I choose the boundary, what the system is and what the interfaces are to the context. So I could ask, is the electronics a system? Or is the whole industrial press a system, which means I'm only interested in the interface to the operator? And if you look at that, there are interfaces everywhere. Whenever we do a choice here, you see it cuts these lines. And cutting these lines means you generate an interface that way. And therefore, I believe when you do that, if you study a system, and these are all valid views and valid definitions of what you consider a system, but it depends what you want to develop and where you are responsible for. And every time you do it, you create an interface. And we will be very careful about these notions of interfaces. So if you look at a system in its operational context, we consider the system as being selected, system under construction or system of interest, and there will be surrounding parts which will be context systems, which will be humans, can be system in the cyberspace, or can be the physical world. And when we create systems and we want to develop systems, we have both to describe systems and the interfaces of the systems and to understand the physical world surrounding the system, the physical and the digital world surrounding the system. And now I give you my definition of a system, which is interesting because you can compare it now to this draft in COSE definition. And we have, it's not very complicated. We have worked a long time on this definition, and now we are quite convinced that this is at least a useful way to look at that. So what is a discrete system model? You can generalize it to a continuous or analog system model. It's not a big deal, but I will concentrate to start with on the discrete system. So there are a number of important aspects. First of all, a system has a system boundary, also called its scope. And it's very important to be very clear about the system boundary. There are a number of reasons for that. I've seen a number of developments where people were not completely sure about that. This is a difficulty in system development. But in the end, if you want to do a very precise process of system development, it's very good to think, first of all, what is a system boundary? And this determines what is part of the system and what is outside the system, which is called its context. The next step is you think about an interface, because when you have decided about the boundary, you already implicitly have decided about the interface. Because whatever you consider of the real world as a system, then you can ask the question, what is the relationship between what's going on inside the system and its context? And this is exactly what the interface is. And since we are dealing with discrete systems, I will go for a very direct definition of an interface. The interface, as I told you, is determined by the system boundary. And the system boundary determines what ways of interactions, or if you like, actions, between the system and its context are possible. So what is in principle possible between the system and its context? And a good example would be a bank machine, a teller machine, which allows you to get money. And this is a system. And if you consider this a system, and then you have usually a very clear understanding what the boundary is, then you can ask what are the actions that are possible between the user of such an ATM and the ATM itself. And then you can define what actions are possible, and this gives you what I call the syntactic interface. I will give you a formal model of that in a minute, but for the moment, I think it's important also to have an informal understanding. Now, having done that, then knowing what are the possible interactions between the system and the environment, which in principle, as I will put it, are actions which could be done by the system, and actions that could be done by the context, which will influence the system, and the actions of the system will influence the context. This is not enough, because if we know that, it would not be possible to operate an ATM. Because we know if we want to operate an ATM, we have to understand which actions we have to do to achieve what we want to do, and what are the reactions of the system, the ATM, and what are the actions an ATM can do. And this is classical, because we deal with this problem, at least myself, I deal with this problem every day, because if I use a new piece of software, one of the question is, what can I do? And what is a meaningful way to use the system? And if I do an action, what would be the reaction? And if I understand that, what do I understand? I understand the logics of the system. So I understand how these different actions work together. And so I have to understand what I call the interface behavior. Some people call it the dynamic interface or the interaction view. I will use the term syntactic interface to describe what are the actions that are possible, and the term interface behavior to describe what are the logics that is to be understood to understand what we can do with a system. In principle, this is enough to define a system related to its environment. But of course, we are also interested to look inside systems. If we want to use an ATM, this is enough. If we want to build an ATM, or if we want to maintain an ATM, we also have to understand how it is structured internally. And after a long time, we came up with just two ways of structure which are of interest. The structuring of a system can be done into subsystems, which we call the subsystem architecture. And it can be structured into states and state transitions, which we call the state view, or just talking about state machines. What is also relevant is this is not an exclusive OR. It can also be an AND. So it's absolutely meaningful to structure a system at the same time into subsystems and into state transitions. And I will introduce a system model where you can study systems both hand in hand with architectures and state transition views. There is, of course, more to that. You can talk about a quality profile of systems. I mean, I will say a little bit about that, but it's not in the center of what I'm talking about. And of course, you have to use a data model, because in the actions, a lot of data are of interest. And we will not talk about deeply on that. We just assume that we can model data. Questions? Yeah?
I was wondering on your choice of discrete system models.
Uh-huh.
Maybe you could elaborate since CPS.
Oh, it's very simple. I will extend it. I will extend it to continuous systems. But to keep it simple to begin with, I was just talking about discrete. And I will show you how to extend it to probabilistic and to extend it to continuous systems. I will not talk more about continuous because there are a number of lectures on continuous systems, but it's a straightforward way to extend it. Yeah?
It's curious that you separate data from states. Are they not entangled in some sense?
Oh, they are, of course, but not only data, but also interaction. Where do data occur? They occur in interactions. And by the way, this is the reason why I use discrete here, because I talk here about action. If you talk about a continuous system, it's not so easy to talk about action. And therefore, to keep it simple, I talk about action. And of course, if you look at action, data are part of action because you do an action. For instance, you insert your card into the ATM. And that means there's a lot of data on your card which is available now to the ATM. And then you have to understand the data. So you have to have a data model of the card. Right. And of course, if you look at the state of your ATM, then after having done some steps with the ATM is in a particular operational state. And the operational state means that it knows your card and it knows your PIN and so on. And it knows perhaps how much money you want to have. And this is all data. And therefore, this data model occurs both at the level of interactions and at the level of states. Right. So we have now these system views, which I call the operational context view, the behavior observational context, the interface view, the system interface behavior, and the interactions between both of them. And then we can have an architectural view and a state view. And perhaps a diagram, a picture is useful there. This is what I call the system under consideration. There's an interface between the system under consideration and its context. By the way, the context, if you look at carefully, viewed from the system, it's also a system. So this is a system and this is a system. And this is very important to have this understanding because it means you can use exactly the same modeling techniques to model the system under consideration and to model the context. And if you do both, you understand that now they interact when you compose them by interacting through their interfaces. And there's an interface of the system under consideration and there's an interface of the context. And if you put those two interfaces together, you get the behavior of the composed system, the system composed with its context. And if you do so, and I keep it very simple here, you can do context observations. And for instance, if you're interested in functional safety, you say, if I model the operational context, more precisely, I should say the interface of the operational context and the interface of the system under considerations, and I put them together, and I will show you that I can do this with a logical AND, then to prove that there's no hazard, I want to prove that from this properties of these two interfaces, I will be able to prove that there is no incident observable for the operational context. And this is functional safety at its kernel. And there are standards of hundreds of pages which basically just capture this. So in this approach, you can immediately start to go into questions like functional safety. Questions here? Now, let's talk about basic system concepts, interface view. Now I give you a formal model of that. And here is a formal model. We worked hard for a long time to come up with a formal model of system which we consider very simple. I'm not sure whether you immediately agree that it's very simple, but very simple means it should be simple enough that we are able to teach it to engineers. We have worked for a long time with different models. We're working with domain theory and And you can also work with category theory and stuff like that. But if you start to teach to engineers, and I'm teaching to engineers every now and then, and you start and you say, first I start with category theory or with domain theory, you have lost them immediately. So you have to have a very basic, simple understanding of a system. And I give you one formal system model, and of course there are others, but we work with this for a number of reasons, and I also will explain to you why we work with this, because it allows you to do a lot of the stuff we are interested in system design. Maybe you look first at the graph. This is a system, and it's along the line what I've already introduced. So we consider a system which has input channels. Here you have an input channel, and an input channel has a name, and it has a data type. And here the data types come in. And it has an output channel. Here you see an example of an output channel. It has a name, and it has a data type. And if we collect all the channels, input channels and output channels, which I did here. So we have two sets of type channels, the input and the output. This is enough to describe the syntactic interface. So the syntactic interface tells you which channels are there and which data can be used as input or as output to the system. Okay? And if we had time now, we could sit together and do an exercise for 2 hours and to describe the syntactic interface of a ATM. And of course, first of all, we have to capture all the data elements that are included. And then we have to understand what are the principal actions that can be done. And what is an action here? An action here is sending one data item on a channel to the system, which is an action of the context. And an action would be to send a data item by the system on an output channel. These are the actions that are possible. And then we could describe an ATM in terms of those actions. But coming back, this is already describing the syntactic interface, set of input channels, set of output channels. I use this notation to say this is a syntactic interface. Okay? Now, I told you that syntactic interfaces are not enough. We also have to look at behavior. Now, let's start to look at behavior. And we decided about 15 years ago, in a work I did together with a very nice Norwegian scientist, Ketil Stølen, who is in Oslo now, we decided to use a model where we introduced time from the very beginning. And I could also give you a number of reasons why this is a good idea. And a lot of people at that time were struggling with a number of difficult questions. And some of those questions get much more easy if you use time from the very beginning. You ask, why discrete systems? Well, this is the reason I can use a very simple model of time. What is time for me? It's just the natural numbers. Maybe that's not enough to say. I understand time as intervals, one interval after the other. And if I now name the intervals by numbers, so I have a first interval, a second interval, a third interval, this gives me a very abstract notion of time. And first of all, I give you a model for what's going on a channel. And what's going on a channel when a system operates, it creates a stream of data. So it depends on the data type. And a stream here is a mapping from the naturals onto T star. T star denotes the set of sequences over T. And it means I model for every interval for a channel the sequence of data that is communicated over that channel. And this is a very convenient model because it includes the empty sequence. So it can happen that there is no communication on a channel at a certain time. And this is very important because when we did that work 15, 20 years ago, a difficult question was for people that didn't have time explicitly in their models. How could you model reaction to a situation where nothing happens? If you don't have time, you cannot really model properly that nothing happens. And this is here very straightforward. So it's a simple model that allows it immediately to say, if there is not an input at time interval 255, I will react to that. So you can also react to actions that do not happen. Having had this, of course, the next step is simple. If you have a set of channels, we can immediately associate behaviors with that, because we just map every channel onto a stream of data. And I'm a little bit, should be a little bit more careful, but this is too much notation. So of course we assume that for every channel we have a stream according to the data that it is supposed to carry according to the definition of the channel. Yeah?
Can I ask a question? What would be the relation between the sequence of things that I've received at time n and time n plus 1?
We come to that.
Okay.
Give me just a little bit of time. I will talk about that. But this is a key question, of course. And having this, I can immediately describe behaviors. And a behavior for a system with this syntactic interface is denoted like this. And it's a mapping of, and I should first explain that. I call this the histories for a channel. So the histories for a set of channels are valuations for each of the channels by a time stream. And so an interface behavior is a mapping that maps a history for the input channels onto a history for the output channels. And to be a little bit more flexible, I introduce a mapping which is not just a mapping between one input history to one output history, because sometimes I want to describe non-deterministic systems, and so I choose a mapping between input histories onto a set of output history. That's a power set. And this allows you to describe non-deterministic systems. By the way, of course, this is equivalent to introduce a relation. So a behavior is a relation between input histories and output histories. I prefer to write it as a function, because I want to express, and this is useful in many respects, that there is a difference between input and output. And we'll come back to that, and this is very much related to your questions. Questions here? Yeah?
This type doesn't limit us to causal systems.
That's right. Thank you very much for that question. This is just what I introduced, so causality. Okay? And what is causality? Causality is a very interesting notion. Causality is discussed a lot by other disciplines too. You can talk about causal system in physics. What is causality? Going away from this formal model, causality is the idea that there is a cause and result of the cause idea of all the things we consider. We would assume that the light will not go on. It will go only on if we switch on the light. And so there is a causal relationship between the switch and the light in both directions. If we have a correct system, if we switch the light on, we can be sure that the light goes on. By the way, also we don't realize that, but there is a little bit of time it takes until when we switch on the light until it goes on. And if the light goes on in a correct system, we assume, which is done in a way where we assume causality, then we know that somebody switched on the light before, but it will not go on without switching it on. Another interesting example is an elevator, which you can also discuss from a causal point of view. And I believe our world is causal. Things happen according to other things that happened before, and if certain things happen, other things will happen later. This is crucial sometimes, But that's how the world is. And so this is exactly according to the questions. We have to bring in causality into our system model. And this is what I do here. I have introduced this syntactic interface. And just to explain the notation, this histories for a channel set I sometimes write with a C with an arrow on top of it. So this is a syntactic interface of a system. This is a semantic interface. And now I introduce what I call strong causality, and I can also explain to you weak causality. What is strong causality? Strong causality is exactly what is in this formula. It says, consider two input histories, X and Z. Remember, input histories are streams, time streams for every channel. To keep it a bit simple, just let's assume we have just one input stream, then it's easier to explain. So if I have now two input histories, as two streams, I ask whether they are the same until time t. X down arrow t means the prefix of history x of length t, and so it means until time t, these two histories are identical. And if these are two identical, then I require to call a system behavior strongly causal, that all the possible output histories I get for x and all the possible output histories I get for z are the same until time t plus 1. So if there is no difference in the input till time t, there is no difference in the choice of the output until time t plus 1. And this is what I call causality. Does it capture your notion of causality?
I think so.
Yeah. You could also get rid of the plus 1. What does it mean that if I get rid of the plus 1? Now we are in a very interesting situation, because we are in the situation where we have a formal model. This is just mathematics. And we think about the real world. And we have to understand how what we decide here relates to what's happening in the real world, which we want to model. Sorry, you had a suggestion?
I thought that instantaneous causality.
Yeah. The difference is that if we take that thing away, it means that we can react to input at the same time. This is what is called instantaneous reaction. Is anybody here who knows STRL? A little bit? STRL was an approach which was only taking, I call it weak causality or only causality, had this causality. And this has some consequences. In the case of what I introduce, I could sometimes work with weak causality and sometimes with strong causality. It has certain additional consequences. But you would have causality, at least weak causality in any case, because if you would have a system which is not weakly causal, it would mean that the system can react to something, to input which comes on in the future. By the way, it would be wonderful, it could build those systems. And I would be a rich person if I could do that, because it would mean that I could predict the future. But this is a physical property of the systems that we consider that they are causal. I will not prove it. Actually, I cannot prove it, because it is a deep question about the real world, whether it's causal or not. But when we build systems, we very, very much rely on causality, because if causality wouldn't be there, we couldn't say anything about reactions. So causality is an issue. We will come back to this in an example which will show why this causality is so important for systems, also for reasoning about systems. But first, let's talk about the specification of interface behavior. And by the way, which is also important for me, I said at the beginning, I want to keep everything as simple as possible. Maybe you don't agree to me, because to think about what I introduced takes a little bit of time, And it doesn't look so simple as I said, but nevertheless, keep in mind I just used 1, 2, 3 slides to introduce the system models, the system interface models. 3 slides. And now we can write specifications. And what is a specification? Well, you can write it in a graphical way, or you can write it in a textual way. I introduce a component, a system I should say, which I call transmission system or transmission component, TMC. TMC has, to keep it simple, just one input stream and one output streams. Both streams work with the same data type. I'm not defining the data type really. And I give you a specification. And to keep it a little bit more interesting, I do not explain the system to you. I just give you the specifications. And then we see whether from the specification I give to you, you can develop an understanding what the system is doing. Well, this is exactly the same notation. Input, one stream called X with the data type T, one stream which is an output stream called Y with the data type T. Here is the specification. That's the syntactic interface. Now we talk about the semantic interface. Semantic interface says there's a relation X twaddle Y between input and output. And of course I should give you the definition. The definition says the following. For all data in my data type, and I have to introduce this notation to you, this means the number of occurrences of the message M in X, which is a natural number or can be infinite. This number and this number are the same. So you find the same number of messages for each message in X and in Y. Full stop. This is the specification. Is this an interesting system? Not?
No, just possible.
Oh, there are a lot of companies which are building those systems and use a lot of money. This is transmission. If you send email messages, if this is your out message and this is the in message of the guy you are talking to, you want to be sure that every email message you send is received. And if you send it several times, it's received several times. And if somebody receives an input message, it was one that was sent. So it's perfect transmission. And if you had time, maybe you have time, you can do an exercise. Take your favorite system modeling approach and write this specification. And if you write this specification as a state machine, you would realize that it's not so simple. And the reason is obvious. We have a specification, we have a specification name, input channel, output channel, and interface assertions. And the key issue here is, and by the way, I have always introduced, and you can have the slides of course, I've introduced some readings if you want to read that. I introduce safety properties and liveness properties at the same time. I don't have to distinguish. Here I have a safety property. A safety property is saying if there is a message in Y, so if there is a message in output and Y is a proper output, then this implies that this message was also in the input. And I can also have a liveness property. If there is a message in the input and Y is a proper output, then this message is also in the output. Safety and liveness. And this specification allows you to introduce both safety and liveness properties at the same time. Frankly speaking, we have done a lot of examples with that and also specified some practical systems on it. Of course, it depends on what type of system you describe, how easy it is to write those specifications. And for complicated systems, specifications can become very, very complicated. And then you need additional structuring, which I don't have time to talk about. But if you are interested in the basics says, this way I can describe any system. It has expressive power, which allows me to describe all the properties of systems I'm interested in. questions. Yeah.
How do you specify time here?
Time is implicit. If I talk about, and I will come back to that, if I talk about transmission of messages as an email client, maybe I'm saying I don't care. If I send a message, it will arrive sometimes. Of course, this is not very useful sometimes, so we better introduce timing bounds, which I will show you.
You mentioned you also include a timing.
Yeah, yes, and I will later show you. Here I have time in the model, but I don't use it in the specification. And by the way, the Italian mailing system was doing exactly the same. I can report about a friend of mine was sending a book to an Italian colleague in 1981, and he received it in 1989. No time bounds, no time guarantees. This is not there. And by the way, again, it has to do a lot with the way you describe systems, because at a certain point you might not be interested in bounds, but you're just interested in some logical other properties, which are shown here. And later you can introduce bounds, which I will show you. Okay? More questions? Just time enough to look at an additional interesting thing in causality. Well, if you look at the specification I've written here, I just use a very simple example. Let's assume I have a stream of messages which I write like this. I have no input here, I have no input here, I have no input here, and in the fourth time interval I get an input of a message M. And then there is no input until the end. And I write an output, and the output looks like this. I get the message M, and there's no input here and no input here until the end. Is this a pair that fulfills our specification?
Well, I thought that you are assuming that you have strong causality, right? So
Thank you for this answer. So the answer is absolutely right. It does not fulfill the notion of full causality. If I do not say anything about causality here, does it fulfill it?
Yeah.
Yes. This means if I take the specification literally, as I wrote it down, it would allow funny behaviors, which is a transmission, which is exactly an email client I would like to have, which delivers a message before it was sent. Wouldn't it be nice? But of course, this is not very realistic. And therefore, we are interested to take care and take advantage of causality. And here you see the proof that if we, in addition to the specification I've written, assume causality, we can now prove that this is not a proper output for the input X. Because here, using strong causality, we just have to choose a particular output which has a property that after time t it has no input anymore, and then from the causality point of view we can show that if we have input until a certain point and seen all the output, then we will see no more output in the future, because this is a property we can derive from causality. So causality gives us immediately a proof rule that allows us to prove that for a specification like this one, which not considering causality would allow us to assume that these are valid input and outputs, would allow us to rule out those. And by the way, what is nice is that, of course, if we are proving properties about this system like the properties I've showed you here, I can prove that without causality assumptions. But if I want to prove properties like the one here, that if I see no more input, I see no more output, I have to use causality. Okay? Questions? I think this is good time for coffee. Thank you very much.